Let me start again. Hi everybody, welcome to week 9. Gas laws is supposed to be week 10, but I lost the presentation that I made for equilibrium and thermodynamics, so I'll do that last. So we're going to look at gas laws today. Very exciting topic. But it's interesting to understand gases and why they do what they do. Gone over a little bit of gases, but gases are effectively, when they're by themselves, they're so small that they don't exist. So, go over a little bit of chemistry of gases. Hopefully you're watching along on the slides. So we have the solid, so the particles in the solid particles are arranged in a uniform distribution, and there's little movement of the particles are very still, they're not really moving. We add some heat to that, we get a liquid. So ice, very rigid, very still. We add energy in the form of heat, starts to vibrate. Particles are not so uniformly distributed. The energy level is increasing, they're bouncing off each other, but they have a defined volume. Solids have a defined volume and a shape, and defined shape. Gases have no defined shape and no defined volume. So they're all over the place, bouncing off each other. And when gases go up into the air, you spray a can of deodorant, they will try to get as far away from each other as possible. So when we have a hot air balloon, we're using gas. Soft drink is carbon dioxide. And when you bake a cake and you put baking soda, plus buttermilk equals carbon dioxide in the gas form. So it produces the bubbles, the fluffiness of cakes. These are all examples of gases at work. So, some important distinctions and characteristics that gases come under. I will share this so you can read them again. Not drawing any of this. Highly compress. You can compress a gas and decrease its volume. If we remove the external force or the compression, then the gas volume increases back to where it was. And this is important, when you heat a gas, it expands. When you cool the gas down, it contracts. Now, it's important to remember. So gases also have high viscosity, so they flow a lot better than liquids and solids. And they have low density. And gases, I don't know if you remember, talked about solubility. And they will mix together in an indefinite manner, whereas liquids you can only mix so much two liquids together, two gases that are miscible together. They can keep mixing indefinitely. You won't reach a saturation point. So we have this wonderful thing, and it's a formula that can tell us the pressure, the volume, the amount, and the temperature based on the other three properties. So the pressure, and I'll stop sharing. Pressure is the force exerted by the gas on the walls when they bounce off it. So that's why when things are put under pressure, they bulge, because it's literally being put under pressure, or because of the force that the gas particles bounce off the walls with. When you increase the pressure, things start to bulge, and that's because the force at which the molecules are hitting the wall is higher. We can look at the volume, which is the amount of smoke. At one temperature, the gas takes up this much. If we increase the temperature, the volume of gas increases. So it will try and fill up the entire vessel. We have the amount, and hopefully I've gone on about moles enough of what they are, or the amount of gas that's in there, and then we have the temperature. So if we look at these, we can predict the properties of the gases and how they will interact and how they will react. And by the end of this, we will get to the ideal gas law, and we can predict the pressure, volume, moles, or temperature of a reaction or a vessel based on the other three. Now, we went through this in week 1. So pressure, we're on slide number 5. So pressure of a gas pressure equals force over area. We measure pressure in torr, so 760 torr, atmosphere, and kilopascals, or pascals. So this is the pressure readings at sea level. We have, this is what we call the standard pressure. So 1 atmosphere of pressure, you go up a certain height, and you get to 2 atmospheres of pressure, and your ears pop at 3 and 4 and 5 and 6 and 7, and same if you're going down with the work. There's another one, the old school way of 760. And that's how far mercury is compressed inside a barometer. So there's liquid mercury in here, and as the pressure gets greater, the level of the mercury will drop. And you measure that in millimeters H2. So volume V. So pressure is P, volume is V, and it's the three-dimensional space. Three-dimensional space. It's sometimes measured in meters cubed, which baffles me. Well, but for simplicity's sake, often just use the liter. Liter is not capital L. It is. So the volume of a bottle of Coke is 2 liters. The mass and the size is different. So we now have PV. We now have the moles. So this is the amount of substance. And it's not measured in grams or kilograms. Sorry, writing a note to myself on the whiteboard. So this is the SI unit for the amount of something. So the international standard unit is the mole. So if we're given the amount of something in grams, we take the amount of substance, or the mass of the substance, we divide it by the molar mass, which is the product of the molar masses of all the elements that make it up, which can be found on the periodic table. So this is N. Don't know if anyone recognizes the equation that I'm building. Told you it will come back to haunt you. So the temperature, fairly self-explanatory. Now, we don't use degrees Fahrenheit. We don't use degrees Celsius. We use Kelvin. Or K. When we're converting from Celsius to Kelvin, we add degrees Celsius plus 273.15. And that gives you the temperature in Kelvin. Kelvin is, again, the international. So that's T. Then we have the ideal gas constant, which is in there. So that's our ideal gas law. How did we build this gas law? Well, lucky for you, I'll explain that to you. I know, right? How exciting. Boyle's law. So to get to this, like when we went through the atomic theories and how we got to what we have now, we had lots of different laws to get to this one. We didn't just come up with this. So this is the relationship between pressure volume. So what he discovered was that when he looked at this relationship, it had an inverse relationship. So think of an inverse relationship. One goes down, the other goes up. One goes up, the other one goes down. So you increase the pressure, P, you decrease the volume. When you increase the volume, you decrease the pressure. So this is Charles Boyle's contribution to the law. So inverse relationship between pressure and volume. You increase the pressure, you're decreasing the volume. So we look at the diagram here, the really bad one I found on the internet. We double the pressure and the volume reduces by half. Double the volume and the pressure decreases. Again, inverse increases by the same amount and decreases by the same amount. So again, I won't go too much into this because it's not hugely important, but you can use Boyle's law to predict the interaction between pressure and volume. So P1 V1 equals P2 V2. So that's if we know the starting pressure, the finishing pressure, and the finishing volume, we can calculate the starting volume. And we can calculate any of these. So P1 V1 equals so we can, if I didn't know this, the starting volume, I could use this equation to rearrange it. But again, we don't really use it. It's just a good way to introduce the ideal gas law. So now we have Charles's law. So this is he said that there is a direct relationship between temperature and volume. So direct relationship meaning when you increase one, the other increases. So if you increase the temperature, you increase the volume. When you increase the volume, you increase the temperature. So increase temperature, you also increase the volume. You're making the particles more excited and they're bouncing off each other even more, so the volume increases. So that's Charles's law. So he looked at T. Charles' law done. So you can see that as you increase the temperature, oh, hang on, share that along here. As you increase the temperature, the volume increases in much the same fashion. So there's a direct relationship or a linear relationship between temperature and pressure. When you raise the temperature, the pressure increases as well. So you can see that here. And here's where we're now looking at a bit more complicated. So this graph, you can see on there that as the pressure goes up and the temperature goes up, as the pressure is going down and the temperature is increasing, so is the volume. So now we're looking at the pressure, the temperature, and the volume. So now we're getting close to this ideal gas law, which is where we are now. So partial pressure, or Dalton's law, partial pressures. He's a pretty smart guy. So if we look at the air, just going to use approximates, it's easier, is 70% nitrogen. Sorry, 79% nitrogen. 20% oxygen and 1% other gases. If the pressure is 100 kilopascals, then each of these gases is exerting, so nitrogen will be exerting 79 kilopascals, oxygen will be exerting 20 kilopascals of pressure, and 1. So the total of, so this total should equal the total of the gas, or these are called the partial pressures. So I think I put that slide in the wrong order. That's good. It's really lame. So if you look at this one, the partial pressures as well, you've got a few, why do I keep pointing at it with my finger? So you have gas 1 and gas 2, or pressure 1 and pressure 2. You combine the two gases and the total pressure, so you can see that, let's say that's 10 and that's 50. Then if you combine them in a container, the total pressure will be 60. 10 exerted by the first gas, you can see there, and 50 by the second gas. So it's the partial pressures of the individual gases. Okay, so kinetic, it's a giant wall of text here. The kinetic molecular theory gives us this ideal gas. And we create an imaginary gas. This is our, I don't know, salt gas. And it's imaginary. But we have made it to behave exactly like the sum of all of the real gases. So this number here, R, is an approximation of all of the gases. And this is one thing that's always annoyed me, is because this is an approximation, then the answer is always wrong. But it's right enough to be right. And it bugs me every time I talk about it. So these are calculations with this gas law are always wrong. But they're as close as we're ever going to get. Because we have to make approximations. Sometimes we never get a perfect answer that we want or need in science and chemistry, fortunately. So that salt gas is our ideal gas that doesn't actually exist. So it takes into account I'll stop sharing so you can. 3 assumptions. That gases are composed of particles. Usually molecules or atoms. They are small hard spheres. They have an insignificant volume, meaning one gas molecule by itself doesn't really exist. Because they are so far away. And they do not attract or repel each other. They simply bounce off each other. So, constant random motion. There's no way to predict the movement of particles in a gas. They move in straight paths. So there's one here, and they will move on straight paths until they collide, and one goes that way, that one goes that way, and then they'll continue on another straight path until they collide, that one goes that way, that one goes that way. And they do this until they're so far apart from each other that they do not exist anymore. So, this is where it's a bit up in the air. Perfectly elastic collisions, meaning that the energy from one particle is transferred to another. And the total amount of kinetic energy remains constant. So these are our 3 assumptions about the gases. There's only forces between them when they collide. So, a kinetic molecular theory for an ideal gas states that all gas particles are in random, constant, straight line motion, separated by great distances relative to their size. So these things are 10 to the minus 5, sorry, 10 to the minus 9 in size, so they're a billionth of a meter. And that may not, the large distance between, we're not talking kilometers here, we're talking, could be meters. But think because they're so small already. They don't have attractive forces between them. And in a system, when they're bouncing off each other, they don't lose any energy. Total energy stays the same when they're bouncing off each other. They're just transferring the energy between the particles as they're bouncing. So that's our 3 assumptions or more than 3. The 3 main headings of the assumptions for the ideal gas mod. Now this is where it doesn't work. When there is low pressure and high temperature, at high pressures, the law doesn't quite work. When there is very low temperatures, these gas molecules will have an attractive force. Dry ice, liquid nitrogen, liquid oxygen is about minus 180 something, I think. So outside of these ideal conditions that we test the gases in, this law doesn't work. So, quick little go over of PV equals nRT and what it means. So, at ideal or normal conditions, the pressure times the volume is equal to the moles of gas times the ideal constant. That's our made up gas number times temperature. I'm going to put on the ideal gas video. So I'm going to put up how we can calculate for P. So if we don't know P, we can calculate for P. If we don't know V, we can rearrange for V. We did this in week 1. If we don't know N or T, then we can calculate for it. So I'll put that video up in the next day or 2, until tonight actually. And then I want you guys to have a look online, have a look back to that first week, and tell me how we can solve for P, for V, for N, and for T. If you can't do it, that's cool. I will go through it in the video. But that is everything for this week. So thank you for watching, and I'll put the recording up and some videos as well.